You know that feeling when you're faced with just a massive amount of information and you wish you could just like instantly grab the key insights?
Yeah, absolutely.
Well, that's what we try to do here. Today, we're digging into some really fascinating research. It tackles a huge question in computer vision. Is there one single, scalable way to train AI so it gets really good at, well, all sorts of visual tasks?
Exactly. It's kind of like the search for the holy grail of visual pre-training.
Mm.
So our mission today is to unpack this new approach. It's called the Perception Encoder, or PE. We'll be looking at the main research paper, obviously, but also the figures, tables, and even some video examples they included.
And the core idea here, which is frankly kind of mind-blowing, is that if you train a model just to understand how images and videos relate to text descriptions, it somehow, surprisingly, learns features that turn out to be useful for a whole bunch of other specific visual things you wouldn't necessarily expect.
Yeah, it's a pretty counterintuitive result on the surface.
Okay, let's unpack this then. Where do we start the old way of doing things?
Yeah, let's set the stage. So traditionally, if you wanted top performance on different vision tasks, like recognizing objects, finding where they are, tracking them in video,
Right.
you often had to stitch together multiple specialized techniques. Each job needed its own custom approach, almost.
It sounds complicated, like needing a different specialist for every little visual problem.
Exactly. And the real problem is, as we want AI to do more complex visual stuff, trying to combine all these specialized methods just doesn't scale very well. It gets incredibly complex.
So there hasn't been that one simple, scalable pre-training method that just works really well across the board?
Not really, no. That's been the missing piece. And that's precisely where this Perception Encoder, PE, comes in.
Okay.
It's a different take. The core idea revolves around global vision language contrastive learning.
Contrastive learning meaning it learns by comparing things.
Yes, basically. It looks at a bunch of images or video frames and a bunch of text captions. And its main job is to figure out which caption correctly describes which visual input. It learns the correspondence. And critically, it does this for both still images and videos.
So when the researchers were building PE, what were the big hurdles they were trying to overcome? What were their main goals?
They had two primary objectives, really. First, scalability and data efficiency. They wanted to make this contrastive training work better, get more bang for the buck from the data, you could say, avoid needing tons of labels for every single downstream task.
Right, make it more practical.
Exactly. And second, they aimed for a truly unified model. One single architecture, one set of weights that could handle both images and videos effectively.
And then came the surprise you mentioned earlier.
Yes, this is the really cool part.
Yeah.
After they built this powerful contrastive model, they looked inside, essentially, and they found something unexpected.
What was it?
Well, they discovered that this model, even though it was primarily trained just matching visuals and text, it had spontaneously learned features that were really well suited for a whole range of specific tasks. Things like reading text in images OCR, answering questions about images, grounding language in specific image regions, object detection, even depth estimation, and tracking objects in videos.
Wait, just from learning image text pairs, it figured out depth and tracking?
Kind of wild, right?
Yeah.
And what's more, when they took these features directly from the PE model, without any extra training for those specific tasks, just using it as a frozen feature extractor,
Yeah.
it performed as well as, or sometimes even better than, state-of-the-art models that had been specifically pre-trained using methods like image captioning or spatial self-supervision for those exact tasks.
That is genuinely surprising. So it learned these task-specific abilities implicitly.
It seems so. The contrastive objective forced it to learn really rich, general-purpose visual representations.
Okay, so how did they actually build this thing? What's the recipe for the core PE model?
Right, the P-core. They started with a solid base, a model called CLIP, specifically the OpenCLIP VIT-L14 variant. CLIP is already known for being good at image text understanding.
So a strong starting point.
Definitely. Then they meticulously tuned the pre-training process. The goal was maximizing performance on a specific large data set, 2.3 billion image text pairs they curated, using a method called MetaClube, but importantly, within a fixed compute budget, around 1 ZFLOP, which is a lot of computation, but still finite.
And what did that basic training look like?
So the baseline setup involved a pretty large global batch size, 32,000 pairs. They used a class token, the AtomW optimizer, and trained it until the model had seen 12 billion samples.
Okay, pretty standard large-scale training elements, but you said they didn't just look at standard tests.
Right. Critically, they didn't just evaluate on, say, zero-shot ImageNet accuracy, which is a common benchmark.
Because that might not tell the whole story.
Exactly. A model can ace ImageNet, but fail on slightly different images or tasks. So they focused heavily on robustness. They measured average performance across a set of different metrics, including variations of ImageNet like ImageNet R for rendition, ImageNet Sketch, Derriere Deviled V2 plus ObjectNet, which uses objects in more natural, everyday contexts.
Ah, so testing how well it generalizes beyond the standard benchmark.
Precisely. That gives a much better sense of whether the learned information is truly general. And they found their baseline CLIP model, while decent on ImageNet, showed significantly lower robustness on these other tests.
Okay, so the baseline was good but not robust enough. Then they started tweaking things, like in Figure 2 of the paper.
Exactly. Figure 2 shows a whole series of ablation studies where they changed parts of the training recipe. They tried things like progressive resolution.
Meaning starting with small images and getting bigger.
Yeah. Also, the LMB optimizer, which can help with huge batch sizes, training directly at high resolution, using rotary positional embeddings, or ROPE, to better encode spatial information.
ROPE.
Attention pooling instead of just using the class token. Various data augmentation strategies, something called masked regularization, and of course, different batch sizes.
That's a lot of knobs to turn. What were the key takeaways from all that experimentation?
Well, several modifications significantly boosted that robustness score we talked about. It suggests that while just scaling data might get you higher ImageNet accuracy, achieving true robustness requires more finesse in the training techniques.
Interesting. Any specific techniques that stood out?
Yeah, things like high-resolution training and ROPE seem to directly improve the spatial understanding capabilities of the model, which makes sense.
Okay. And what about data augmentation and that progressive resolution? You mentioned those had surprising benefits.
That's right, they highlighted those. Data augmentation helped, as you might expect, but progressive resolution seemed particularly effective for robustness.
Why would that be?
The researchers hypothesized that maybe the standard contrastive task encourages the model to over-rely on just the global gist of the image, the overall scene matching the caption.
Ah, I see.
By starting with low resolution and increasing it, you sort of force the model to learn more detailed local features early on, preventing it from overfitting to just that global signal.
That makes intuitive sense. Any other interesting effects?
Yeah, one other thing. Progressive resolution and also attention pooling actually shifted, where in the network, the best features for a downstream task like object detection were found. It pushed them deeper into the model layers.
Huh. Okay, so that covers the core image language model. But they wanted it to work for video, too. How did they bridge that gap?
Right. That required building what they called a video data engine. The central idea was to generate really good video captions automatically at scale.
Generate captions, not use existing ones.
Well, existing video captions are often sparse or not perfectly aligned. They wanted high-quality, descriptive captions to use for the same contrastive learning approach. But for video, this engine had three main phases.
Okay, phase 1.
Phase 1 was building a base video captioner. They called it the Perception Language Model, or PLM. They basically took their PE image encoder and hooked it up to a language decoder specifically, Llama.
So PE sees the video frames, Llama writes the description.
Pretty much. And they trained this PLM on a big data set, about 65 million image and video examples, to get it decent at generating initial video descriptions.
Got it. A starting point for video captioning. What was phase 2?
Phase 2 was about quality control and refinement using humans. They took about 120,000 videos, generated captions with their PLM, and then had human annotators review and improve them.
What did the humans do specifically?
The instructions were straightforward. Remove hallucinations or errors, correct inaccuracies, make the captions concise, and add important missing actions or details. Table 3 gives details on this refined dataset called PVD. They ended up with nearly 120,000 human polished captions.
And the paper shows examples, right? Like the cat video.
Yeah, exactly. The human caption for the cat grooming kittens is much richer than the initial AI one. Same for another example, clarifying someone's cutting a pickle, not just a green item. That human refinement adds crucial detail and accuracy.
Okay, so improved captions via human feedback. What's the final phase, phase 3?
Phase 3 involved leveraging a really large language model, Llama 3.370B, for summarization and integration. They fed it the PLM's video caption, plus captions for individual frames generated by another Llama model, and existing video metadata like titles and descriptions.
Why include the metadata?
Because titles and descriptions often contain contextual information, who, what, where that might not be obvious just from the pixels, but is really useful for understanding the video. The big LLM combined all these sources to create even better, more comprehensive final captions.
Clever. So they use this whole engine to generate captions for how many videos?
For 22 million videos, this gave them a massive data set for the next step. Fine-tuning PE for video understanding using contrastive learning.
And how did they actually feed the video information into PE during this fine-tuning?
Surprisingly simply. They just sampled 8 frames uniformly from the video, ran each frame through the PE image encoder to get image embeddings, and then just averaged those 8 embeddings together. That average became the video's representation for the contrastive loss against the caption.
Just averaging, no complex temporal modeling.
Nope. They mentioned that simple average pooling actually outperformed more complex methods they tried. Sometimes simple is better.
Huh. Did they check how much each part of that video data engine contributed? Like, were the human captions really necessary?
They did an ablation study, shown in Table 2. They tested using only metadata, only PLM captions, only frame captions, etc. The results were clear. Using both the video level and frame level generated captions significantly boosted performance on both image and video tasks compared to just metadata.
But were all parts essential?
For peak performance, yes. But they noted that the original video metadata and the PLM's video caption were the most critical individual components. Still, adding the frame captions and the LLM refinement pushed the results higher.
And Figure 6 shows this improvement over time.
Exactly. Figure 6 tracks performance on various benchmarks: ImageNet variance, EOCO detection, video classification like kinetics, video retrieval like MSR VTT, as they fine-tuned PE on increasing amounts of this recaptioned video data, from 0 up to 17 million samples. Performance consistently improves across the board for both image and video tasks.
Okay, so this PE model works for images and video. Did they build different sizes?
Yes, they did.
All right.
They created PE models at different scales: B for base, L for large, and G for giant. Table 4 lays out the parameters, different numbers of layers, parameters, and resolutions they handle. The biggest one, PQG, has 2 billion parameters. It's a substantial model.
2 billion, wow. And for the smaller B and L models, did they do anything special to boost their performance?
Yeah, they use knowledge distillation. Basically, they use the big P-Core-G model as a teacher to train the smaller student models, B and L. They focused on matching the similarity distributions, how similarly the teacher model thinks different image-text pairs are related. The student learns to replicate that pattern of similarities.
And did that help?
Significantly. They found a neat trick, too. Using a lower temperature for the teacher's output distribution during distillation made the process even more effective. It really helped transfer the knowledge from the large model to the smaller ones.
So after all this refinement and scaling, how good was P-Core? What were the standout results?
It achieved new state-of-the-art results across a pretty wide range of zero-shot classification and retrieval benchmarks for both images and videos. Table 7 gives an overview, and Table 8 dives into more detail.
Any specific examples?
Sure. P-Core-G got a huge plus 9.6% boost on iNaturalist, which is tough due to many fine-grained categories and imbalanced data. It also saw a plus 3.0% gain on Dollar Street, which tests understanding cultural diversity in images.
What about that OCR performance you mentioned?
Yes, surprisingly strong OCR on text caps, even though they used horizontal flipping during training, which usually hurts OCR. And for video retrieval on their own PVD benchmark, P-Core-G was way ahead, like plus 13.6% better on text-to-video retrieval compared to a strong competitor, Intern VL.
Okay, very impressive on zero-shot tasks. What about using it as a feature extractor?
Also top tier. Table 8 includes results from probing the frozen P-Core-G encoder using KNN, linear probes, and attention probing on ImageNet 1K. It outperformed all existing open encoders they compared against, even much larger models.
So P-Core is great for general recognition and retrieval, but what about tasks needing precise spatial understanding, like detection or segmentation?
Right, that's a slightly different challenge. While P-Core had good features, they noticed that the best layer for spatial tasks varied depending on the task itself, as shown in Figure 8. One layer might be optimal for detection, another for depth.
So how did they address that, make it consistently good spatially?
That led to PES-Spatial. The idea was to align the model's features so that the later layers were consistently good for various spatial tasks. They used a couple of techniques. First, a form of self-distillation.
Teaching itself.
Kind of. They used features from a specific intermediate layer, layer 41 of PCORI, which seemed to have good semantic information, as a target to guide the final layers. They combined this with strong regularization techniques like drop path and layer scale to maintain generalization.
Okay, self-alignment, what else?
They introduced a locality loss. This used another model, SAM, the segment anything model, as a teacher.
Sam, the one that's really good at finding object boundaries.
Exactly. They distilled spatial correspondences from SAM. Essentially, they encouraged spatial's representation of how different image batches relate to each other to match SAM's understanding of object masks and boundaries.
Why use Sam?
A key property is that SAM's mask predictions are quite robust to changes in image resolution. This allowed them to apply this locality loss while training spatial at its native high resolution, which is beneficial.
So, aligning to itself and aligning to Sam, how did that work out?
Figure 16 shows the layer-wise analysis, aligning just to layer 41, self-alignment, help for detection, depth, and segmentation. But interestingly, not so much for tracking.
Okay.
Aligned just to SAM, conversely, boosted tracking significantly, but actually hurt performance a bit on the other tasks.
So neither was perfect alone.
Right. But combining both teachers aligning to layer 41 and SAM created spatial G. This seemed to lift the performance for all spatial tasks towards the final layers of the network and generally outperformed just self-alignment.
What about tracking? Did it match the SAM-only alignment?
Tracking was slightly lower than the SAM-only version, but still very competitive and much better than the self-aligned or base PCOR model. So, spatial G offered the best overall balance for spatial tasks.
And the results tables confirm this?
Yes, Table 13 shows strong frozen feature results for spatial G on tracking, Davis benchmark, semantic segmentation, ADE20K, and depth estimation, NYU. And perhaps most impressively, Table 15 shows a system-level comparison on CoQ object detection.
What did that show?
Using spatial G as the backbone with a simple DETR-style detection head, it matched the performance of much more complex detection-specific tuned models. It was apparently the first general contrastively pre-trained model to achieve that level of performance on CoQ detection with such a simple setup.
Okay, so PCOR for general tasks, spatial for spatial tasks. What about connecting it to language models for multimodal tasks like visual Q&A?
That's the third variant, PLang. Here the goal was to adapt PCOR to work effectively with a powerful decoder-only LLM, specifically Llama 3.
How did they connect the vision part, PE, to the language part, Llama?
They used a vision projector, basically a small neural network, that translates the visual features coming out of PE into a format that the language model can understand.
And then they trained this combined system.
Yes, in 2 stages. First, a kind of warm-up fine-tuning just on image-text pairs, followed by fine-tuning on a much larger, more diverse multimodal data set containing various instruction-following examples, visual Q&A, etc.
Did they experiment with how best to do this language alignment?
Yes, lots of ablations detailed in Table 9.
Aye.
They tried different LLM sizes, whether to freeze the LLM weights or fine-tune them, different types of projector networks, MLP versus simpler linear, which PE layers output to feed into the projector, and different regularization strengths.
Any key findings from those experiments?
They found that using a larger LLM helped, unsurprisingly. Fine-tuning the LLM weights instead of keeping them frozen was better. An MLP projector worked better than a simple linear one. And interestingly, they found an optimal PE layer, layer 47, to connect from not necessarily the very last layer.
So how did PLang stack up against other models on multimodal benchmarks?
Table 10 provides a big comparison. It shows PCOR and PLang against other popular vision encoders across tasks like OCR, chart understanding, document Q&A, general VQA, captioning, and video tasks. PLang performed very competitively, often outperforming others.
Is this alignment specific to Llama 3 or does it transfer?
Good question. Table 11 shows they tested PLang with a different LLM, QuenLM 2.57b, and PLang still outperformed other vision encoders, including one specifically designed for Quen, demonstrating good transferability.
And the overall system, the final multimodal model.
Their full model, PLM8B, using PLang and Llama 3.1, was compared against other leading open-access multimodal models in Table 12. It showed superior performance across a broad suite of benchmarks.
We touched on this briefly before, but efficient training techniques, large batches, LMB, ROPE, were pretty crucial throughout this whole process, right?
Absolutely. Developing and training models at this scale, especially the core PE model, relies heavily on these state-of-the-art efficient training methods. They were fundamental to making this work practical.
Okay, so let's try to wrap this up. If you had to boil it down, what's the single most important takeaway from this whole perception encoder story?
I think the key insight really is that this relatively simple concept, contrastive vision language pre-training, done globally for images and videos, can be incredibly powerful. It allows the model to learn visual representations that are far more general and versatile than perhaps previously thought.
Right. It's not just about learning captions, it's about learning a fundamental understanding of the visual world that then transfers surprisingly well.
Exactly. This work really highlights the potential for scaling up a single, unified pre-training approach to tackle this huge diversity of downstream vision tasks. The strong results from PCOR, PESPATIAL, and PLang really drive that point home.
It's pretty compelling stuff. Okay, so here's a final thought to leave our listeners with. Given how effective this global contrastive approach seems to be for unifying so many different vision tasks, it makes you wonder, could similar, simple-seeming but powerful learning paradigms unify other apparently disparate areas of AI? And looking ahead, as these models get even bigger and more complex, what might be the limitations or potential pitfalls of relying on such a unified approach?
That's a great question. Definitely something to chew on. Are we finding fundamental learning principles, or will specialization always be needed at some point? Food for thought.